We're continuing our discussion of this metal sphere in the spherical shell. Remember that we have a metal sphere charged to plus Q, and it's inside a metal spherical shell which is charged to minus Q. And in part A, we calculated the potential in all regions in space for r less or equal to Ra, r between r sub a and r sub b, and for r greater than r sub b. Now, let's look at part C. We also calculated in part B the potential of the inner sphere with respect to the outer sphere. Use electric field is equal to minus gradient of voltage and the result from part A to show that the electric field at any point between the spheres has a magnitude VAB divided by 1 over RA minus 1 over RB multiplied with 1 over R square. In part D, use the same equation and the result from part A to find the electric field at a point outside the larger sphere at a distance r from the center, where r is greater than r sub b. And in part E, suppose the charge on the outer sphere is not minus q but a negative charge of different magnitude, say minus capital Q. Show that the answers for parts B and C are the same as before, but the answer for part D is different. Okay, so let's start with part C. We're using the relationship between the voltage and the electric field. Electric field is equal to minus the gradient of the potential. And we have the result from part A, so we're going to substitute that here. So that is minus the gradient of the potential, which is KQ over R minus KQ over R sub B. This was our potential for R less or equal to RA. And this is the derivative with respect to radial distance minus d dr of only the first term, because the second term derivative already gives us 0. It's a constant. So we have kq over r in r hat direction. Now, what is the derivative of kq over r with respect to r? That is kq times derivative of r to minus 1. The minus signs will cancel, so I will have a plus here. And then I will have r to the minus 1, r to minus 2. So this will give us kq over r square in r hat direction. So this is the answer we will obtain. Now we have the answer from part B of the problem. So let's note that the potential of the inner sphere with respect to the outer sphere, VAB, is what we found in part B. It is K times Q, 1 over RA minus 1 over RB. So if I divide VAB with 1 over RA and minus 1 over RB, what do I obtain? 1 over R sub A minus 1 over R sub B. You can see that I will obtain so here is a Q missing. So this was the result we have obtained in part B, KQ 1 over RA minus 1 over RB. So that's what I find here. So VAB divided by 1 over RA minus 1 over RB is K times Q. This is what I see in this equation. Now part C asks me to show that it is VAB over 1 over RA minus 1 over RB times 1 over R square. So I will substitute for KQ VAB divided by 1 over RA minus 1 over RB. So I will find that the electric field is equal to V sub AB 1 over RA 1 over R sub A minus 1 over R sub B, that is KQ, multiplied with 1 over R square. So it was KQ over R square. So it is 1 over R square in R hat direction. So that's the electric field. This is what I was supposed to show in part C. That the electric field here is between the spheres has this magnitude. Okay, so now I'm going to move on to part D. In part D, we're looking at the electric field outside both of the spheres. So electric field is once again minus the gradient of the potential, and the potential for R greater than R sub B is a constant. So what was it? For R greater than R sub B, we found that the potential is 0. So in this region, the potential is 0. Therefore, the electric field, or it's a constant, we could say, for R greater than R sub B, or R greater or equal to R sub B, is equal to 0. In part E, we are changing the charge on the outer sphere and investigating what happens to the answers in part A, B, and C. Now in part A, by using Gauss' law, I have shown that the electric field for R less or equal to R sub A is equal to 0 because the charge inside the sphere is still 0. So the electric field doesn't change and the potential doesn't change. So this is still correct. So the answer does not change for this region. For the region in between the two spheres, since the electric field between R sub A or R sub B is equal to KQ over R square in R hat direction, it is determined by the charge enclosed by a sphere whose radius is less than R sub B but greater than R sub A. So this answer is still correct. So the potential also doesn't change. The answer does not change. For the third region, when we move outside, if I write Gauss' law, E dot dA, closed surface integral, which is E times 4 pi R square, now the charge enclosed, Q in divided by epsilon 0, that's Gauss' law, becomes not 0, but it's going to be Q minus capital Q, because the charge has changed from minus Q to minus capital Q divided by epsilon 0. So this tells me that the electric field for R greater or equal to R sub B will be Coulomb's constant K, Q minus capital Q divided by R square in R hat direction. So I have found that the electric field in this region changes. So I can basically summarize these results. So since I have found that the electric field in the region R sub A are less or equal to R sub B, and the electric field in the region R less or equal to R sub A do not change. The potential in these regions don't change. The answers for parts B and C do not change. But the answer for part D, if I take the potential for R greater or equal to R sub B, now this is the sum of the contributions from the two spheres. The first one, the inner sphere, is kq over r, and the spherical shell is minus k capital Q over r. That is the potential in this region. Then I will find that the electric field is minus the derivative of the potential with respect to radial distance r in r hat direction, which is the gradient. This is the derivative of 1 over r gives me minus 1 over r squared, but there's another minus sign here. So this answer becomes kq minus capital Q over r squared in r hat direction. So this answer changes. But the answer for parts B and C do not change because the electric field and the potentials are the same. All right, so in this part of the problem, I have used electric field is equal to minus gradient of potential, knowing that the potential between the two spheres was given by kq over r. This is the contribution from the inner metal sphere, and minus kq over rb from the outer shell. I obtained the electric field as kq over r squared in r hat direction, but then since I know from part B the potential of A with respect to B, which is the inner sphere with respect to the outer shell, is given by this expression, I can substitute for KQ this expression, which is what I did here, to obtain the electric field written in terms of the potential of the two regions, the potential of A with respect to B. Now, looking at the region outside both of these spheres, I find that electric field equals minus gradient of voltage gives me zero electric field. Because the potential for R greater or equal to R sub B is 0, kq over R minus kq over R is 0. If I change the charge that is on this sphere, so this sphere has charge minus Q, now it has charge minus capital Q. The electric field inside both spheres is equal to 0. The electric field inside the metal is equal to 0. The potential doesn't change also. The electric field between the spheres is kq over r squared r hat still, because you can see the potential is the same. So I will have kq over r. Actually, the potential changes because I will have kq over r minus k capital Q over rb. But since I take the gradient, this doesn't have a contribution. So the derivative of kq over r with respect to r gives me, with the minus sign, kq over r square r hat still. So the answer for the electric field doesn't change, but actually there is a change in potential here. So I can say that for this region, the potential becomes, potential for r sub a, r sub b is going to become kq over r minus k capital Q over r sub b. So the potential actually will change in this region. So that's for this part. Now, the electric field doesn't change. Looking at the region outside both spheres, I will see that because the charge enclosed is Q minus capital Q, Gauss' law tells me that the electric field should be kq minus capital Q over r square r hat. Or using the contribution from the potentials from the inner sphere, kq over r, the outer shell minus k capital Q over r, I see that this potential also changes. Taking the minus gradient of this potential, I find the new electric field, kq minus capital Q over r square, in r hat direction. So to summarize, by changing the charge on the outer sphere, the electric field inside the metal sphere is going to be zero. So I will have a constant potential inside. And what is that constant potential? Well, that constant potential actually is, for this region, Vr less or equal to r sub a, is kq over r sub a minus k capital Q over r sub b. So the potential changes for this region. So maybe we should not say the answer doesn't change. Let's rewrite this potential here to make it more clear. Potential for r less or equal to r sub a is equal to kq over r sub a minus k capital Q over r sub b. It's a constant potential. So since the electric field is zero, the potential is still constant. For the region between r sub a and r sub b, I will have a new potential, V r sub a r sub b. This will be equal to k q over r minus k capital Q over r sub b, using the superposition of the contributions. And for the third region, I will have a new potential, which is kq over r minus k capital Q over r. So that gives me, because this is a constant here, taking the gradient, the electric field doesn't change. But for the third region, the electric field changes. The potential also is different, kq over r minus k capital Q over r. And I can see that the answer to part D will change, because by taking the gradient of this is no longer a constant. This becomes kq minus capital Q over r square in r hat direction.